Hello there, welcome to another video from Aology. So in this video, as I promised, I want to walk through the paper AliBi, train short test long attention with linear biases enable input lens extrapolation. That's why it's called AliBi, attention linear biases and with lens extrapolation. So basically, before going through this paper, I want to talk about what is the um, meaning of the lens extrapolation and what is the meaning of linear biases. Then we can understand what is AliBi. So when we have language model, I'm talking about causal language modeling, just decoder ones like GPT that only look at the previous tokens. And we will talk about like how we can use AliBi for the encoders model or like BERT model too. But let's for now focus on these kind of models. And we know that for passing this sequence to attention based on the attentional unit paper, so we have the output embedding sum with the positional encoding and then pass to the attention unit. So this positional encoding can be defined differently. One way, a simpler way, is like just putting 0, 1, 2, 3, very naive approach. And this is giving like put more attention when we are in this position on the context embedding. We are trying to predict the next token. So we are saying just put more attention on this one, then put more attention on the next one. And when you go past, the amount of attention you want to put on this token would be decreased. That's one way. But that's like not working if you have a larger context because sometimes some of the information we are looking into is not related to that like nearest neighbors. They are related to some other places. That's why in the attentional unit paper you see they mentioned sinusoidal positional embedding, positional encoding, and it's like we have a sinus function, we have multiple sinus function with different frequency, and I think there was a good picture also here. I think this was from Yannick. You can also look at that video that it's explaining very well that how this works. You see that we have a sinus with this frequency with another frequency, and for each token, we will get the values on that place, and we have a multi-dimensional positional embedding that can be combined with the dimensional of the uh, output embedding that we have. That's also another way. But AliBi is doing something different. It's saying that, let me back to the paper. It's saying that uh, one simple thing that we can do is, first of all, instead of applying the summation or multiplication of the positional encoding and output embedding here before applying to the attention, what if we apply the key and query, like the multiplication, on the output embedding, then back to here, then we apply or sum, only sum because they mentioned in the paper the multiplication decrease the performance, but summing up these linear biases as a positional encoding and this matrices you're seeing here is very similar to what we define as absolute, but it is uh, applying it not before going to the attention unit, but it is uh, used inside the attention unit after we calculate query and key multiplication, and then after doing that, we want to just go multiply it by value and normalize it. So this is very simple. This very simple approach works very well, and they show that this gives the model some sort of ability that if we train it on a shorter context, we are able to inference it on the longer context, usually twice of the training context, not more than that. So if we train it like 512 tokens and we use AliBi, we are able to inference it like by 1024. But there is other details I will talk about it, like the steps. This is not just these linear. There are some steps to making these units. But overall, this is really simple and it is really promising. And this is one of the way that it's called linear biases because they are just linear and they just summed with the querying key. And about extrapolation and lens extrapolation. So as I said, so when we say that like put more attention on this is some sort of extrapolation that how I can extrapolate over the length of the text. So using that method, they are saying that for example, if you have multiple attention head, for each attention head, we can use a different step value. So we will have different extrapolation for different heads, and that would give us a better result. So this is just for causal models. We want to also talk about the non-causal and like the BERT or encoder model or even encoder decoder. And there are some quotes that write about it. So if we search like train short test long and we search for the Git repository, we see that the AliBi main repository is here. And they have explained very, very well. And they also answered many questions. Appreciate them for all of this effort they've done. And one of the thing I want to bring it here, it said like here, if you want to apply AliBi on the bidirectional transformer such as encoder, you could use one of the methods here. And I will go through that after we read through the paper. So let's back to the paper. So since the introduction of transformer model by Waswani, a fundamental question has yet to be answered. How does a model achieve extrapolation at inference time for sequences that are longer than I saw I can't read today that are longer than it saw during training? We first showed that extrapolation can be enabled by simply changing the position representation method, though we find that the current method do not allow for efficient extrapolation. We therefore introduce a simpler and more efficient position method, attention with linear biases or AliBi. AliBi does not add positional embedding to word embedding as we discussed. Instead, it biases query key attention score with a penalty that is proportional to their distance. We showed that this method trains a 1.3 billion parameter model on input sequence length 1024 that extrapolate to input sequence of length 2048, achieving the same perplexity as a sinusoidal position embedding model trained on input of length 2048. This is also a very important point I'm mentioning. So if you want to train a model on the longer input, so we need more resources, we need more GPUs, and like in terms of the perplexity that we can get, if we can get it by the smaller amount of sequence lengths, that would be much better. And you see that it's like 11% faster because you are training on the shorter lengths. And yeah, and using 11% less memory. AliBi inductive biases toward recency also led to the outperform multiple strong position method on the Wikitext 103 benchmark. So this is like an abstract of what I have mentioned. And let's see, for example, the different embedding they have tried, and they try to increase the inference input token and see the perplexity, and the perplexity lower means better, yeah. So the model here is trained on 512, and model here is trained on 1024. And the interesting point is that like perplexity is not increasing for the AliBi. Of course, they have mentioned like just use it for 2 times more, but seems like even more than that it's working. That depends on some situation, of course, but for others, like T5 biases, rotary positional embedding, and sinusoidal, uh, you will not get this. Especially look at this one, the first positional embedding, and you see that the improvement that happened during time, over time, for the positional embedding extrapolation. And T5 is very close to the AliBi, but there are some small changes. They also mentioned that they got many inspiration from the T5 and rotary embedding. And I don't want to discuss about those two, but let's see other uh, things that they have discussed here. So about like training speed, you see that the sinusoidal is the best because it is much simpler, and AliBi is also good for input lengths small. But when input lengths go up, so some of the methods like T5 biases are really heavy and or rotary, and the AliBi can outperform these two methods. So these are the things. I don't want to take more time, and let's just talk about these steps. So they talked about this. This M is the value that it said a scalar M is a head specific slope fixed by training, fixed before training. So a slope is something like this value for each head. We can define that. There are different implementation. You can see like some people mentioned that it's better to use 2 in power of n heads and then define that the slope in that based on the like mod of number of heads by 2. So we will talk about that exactly like here. And let's back to the results. So they are again showing for the wiki text result. They got a better result with the longer text. And here is another thing that they want to discuss. So they said that AliBi and sinusoidal model trained on 50K updates on this data. Extrapolating on validation set, AliBi achieved the best result around 2L, but maintained a strong performance even up to 10,000 token in these experiments. So it seems like you can get the best performance by multiplying the input sequence by 2, but still you can get some strong performance even if you increase that a lot. And that is really good. It is like increasing that by 20 times. So, and that's it. I think about the paper, there is no other thing to discuss. This is very uh, clear and very simple method, but very effective. And I want to close this and let's go to the quote. Um, I want to explain this how this works. So they're talking about like in the paper. I think he is one of the writer of the paper. In the paper, we only showed the result on causal language model. We use causally masked decoder self-attention. Yeah, so I forgot to mention this. So uh, when we use AliBi, because we have masked, like if you look at that matrix that I show you, that matrix, it was diagonal because it was a causal model. We don't care about the future, and that can be used as a mask because in the causal model we can use the for the decoder model we can use the mask for the self-attention layer. So it said if you like to use AliBi for sequence-to-sequence tasks such as translation, speech, or T5, or if you'd like to use AliBi for mask language models such as BERT, there are some modifications required. And you can see that they're mentioning here like how many maximum position we have. And we defined a context position and similarly a memory position. These are two similar, but one of them is just row based and another one is the column based. And when we do this relative position, we are getting that matrices uh, which has a diagonal of 0, I guess, and the other parts are the value, exactly the relative position of them. And then it's just like um, unskews it to have a repeat of these matrices for different heads. It's said that the quote correctly generate the full bias matrices. Note that this bias matrix is symmetric around the diagonal since it's compute the absolute distance between the query and key. Just want to show you an example here. I just want to copy and paste that we are on the same page together. So I am supposing, okay, everything sounds good. I'm supposing that for example, I have 7 token and I want to have 4 uh, attention head. Okay, and let's also import torch. Okay, Coda, no kernel image is available. Okay, I have some issue with my Coda, so I'm going to delete this. This is just a simple. Yeah, so you see that we have, as I said, we have all of the 0 in the diagonal, and we have these positions. But what we want to do is we want to define like slopes for each head. So each head can extrapolate for different lengths. And they are talking here about defining slopes. And then we can uh, get the slope based on how many attention head we have, and then multiply those slope with this. So by this, we will get, let me also copy and paste this just to get you some result here, and we can see some of the outputs. I forgot one, oops, I forgot one thing, I guess. Def, oh yeah, I don't know why the def is not there. Oh, okay, it was there, but I couldn't see it. Okay, that's the function. If there is any self stuff like that, I want to delete it. Okay, this was comment, I think, isn't it? No, return unexpected indent. Oh yeah. Okay, so we have this, and then we have the symmetric definition. So it's defining 3 options. One is symmetric, so means that the bias we assign to query and key pairs are plus n or minus n token apart will be the same. Let's just try this. I want to do this, and I'm also want to remove all of the self here. Hopefully this work. Mass is not import. Let me import mass too. Import mass. Oh, again, Coda. I don't want to have Coda here for now. Okay, so we have AliBi, and here is the 4 attention head that we have, and these are symmetric, but you see based on the different slope that we have defined, um, we have different extrapolation for each head. That's one thing. So they also mentioning, oh, it's not done. They also mentioning that, oh yeah, it is done for this one. It's also mentioning for the fair sake library that we can use something else. But for non-symmetric, so it's mean that it doesn't need to be exactly like, for example, when I attend to the next token like this, I don't need to attend to the previous token exactly same. So that's why it's also defining non-symmetric, and this can be used. It's also mentioned here. We can use this this AliBi to the attention function and add it after the query key computation. And another way is this one. So it's using some utils. I'm not sure about that utils, but it seems like it's creating a triangular upper and triangular lower, like the upper level of the matrix and lower level of the matrix. And then we will have the mask over there. And for the upper level and lower level, it's doing the different slopes. That's why it's like non-symmetric. I don't want to go to the detail, but like these proportion shouldn't be exactly like same as when you attend to the previous tokens. Yeah, that's another way. And they're also mentioning with no mask. So it said in this approach we don't use any masking, but instead we make the position non-symmetric by using different AliBi slope depending on whether the key is to the left or the right the query. And this is a different way of doing that without the masking. So it said also for cross attention for translation model like T5, you will also need to implement cross attention. So for BERT models, we have only encoder part, but for like T5, we have encoder and decoder, and there is a part. If you look at this also, we have the decoder and encoder, and there would be a part that we are doing the cross attention here, and that's it's mentioned. That's why it's mentioned attention from the decoder to the encoder. Um, the T5 model uses no positional information in cross attention. So there is a positional encoding in T5 model called T5, and there is no positional information in cross attention. And they all also using the same. So there is no positional information is passing over there. And let's go to the X transformer library by LucidFrame. And I like that because let's see what we have inside the X transformer. I haven't seen this. We are just walking through this together, but I think there should be AliBi positional bias, and we should be able to use it very simple. I'm not sure this is implemented for decoder only or it can be used for both. Let's see. Okay, and can I see an example of using that somewhere? Yeah. So X transformer is really powerful. So what you can do is you can say AliBi positional biases. You can pass that AliBi positional biases through. There are other methods like dynamic positional biases or others. We don't want to talk about it for now, but seems like it should work for all of the encoder decoder. I feel. Yeah. Transformer wrapper. It can be encoder and decoder, but the AliBi. Let's look at the AliBi again. You can also define the AliBi head. I think an AliBi head should be less than or equal number of heads. And let's look at these positional biases again. That's what it's doing exactly here. So we get the slopes. That's cool. And then we rearrange them and we get register buff. We just register them. And for get a slope, it's using the same function I think that we used so far. Yeah, it's using exactly the same thing. So it is not, I think, for encoder, if I'm right. Yeah. So it's have a get bias. So it's do this, arrange that j minus I and j, and j arrange j. Oh, I want to try this. I'm not sure about it, but it's this get bias is used where in the forward function of AliBi positional biases. So it get two position and then we get their biases and multiply by the slope. Interesting. I think it works for both. I'm not 100% sure, but I think it works for both. There should be some example here. Let me check for this one. It said rotary embedding has since been hugely successful, widely adapted in many large language models, including the largest in the world, Palm. However, it has been uncovered in the AliBi paper that rotary embedding cannot lens extrapolate well. This was recently addressed in the Microsoft research paper. Is it the same? No, that is something different. A lens extrapolatable transformer. And I haven't seen that yet. Interesting. And they said they propose a way to unobstructively at the same decay as AliBi and found that this resolved the extrapolation problem. You can see this in the repository by setting rotary expose true. Like AliBi, it would enforce the attention to be local. You can set the receptive field rotary expose scale based. So there are some other method even better than AliBi, I guess, now. But let me AliBi positional embedding. Let me see that. It said these papers propose to simply apply static linear biases to the attention matrix. The authors show it this is not only effective as relative positional encoding, but also allow the attention to extrapolate to greater sequence length. This repository also offers bidirectional variant, non-symmetric, yeah, proposed by the authors. Yeah, as we defined it exactly. However, this is untested. If you need bidirectional extrapolation, the safest option would be dynamic positional biases. Okay, I haven't seen that also. Maybe that's another paper we can look at it. But Lucid Dream is doing a great job on documenting and writing all of this code. Thank you very much. And instead, it may be that AliBi enforces a strong local attention across the heads and maybe hinder it from attending a distance greater than 1K. To avoid any issue with global message passing, I've decided to introduce another hyperparameter AliBi number of heads, so you can specify less heads for the AliBi bias. Another update, there are reports that AliBi outperformed rotary embedding for pre-training and downstream fine-tuning. Oh, interesting. And new papers show that no positional embedding can lens extrapolate even than explicit ones. Wow. The impact of positional encoding on lens generalization. Oh, that is really interesting. That is 31 May 2023. The impact of positional encoding on lens generalization in transformer. And oh yeah, this is interesting. Yeah, I will put this in my queue. Maybe we can read this together. It said that these papers show no positional embedding can lens extrapolate even than explicit ones, which is really, really interesting. Cool. So if you want to use the transformer, X transformer, or the train short test long repository, you're able to do that. Now you know what's happening there. Everything simple. Great. Thank you for your following. Please subscribe, leave a comment, and give me energy. Have fun.